In the previous lectures, we were trying to focus on how the quantum aspects of the nuclear spin can help us understand a measurable. For instance, we defined the wave function as a superposition of states, and the time coefficients here provide how the wave function changes over a period of time. Following this, we also saw how a measurement would help us get the final desirable, which will be the trace between the product of the density matrix, which is nothing but a probabilistic distribution of these coefficients that have time dependence in them. And we were able to see that this time-dependent Schrodinger's equation was converted to the Liouville-von Neumann equation, which gives the rate of change of the density matrix sigma as I times the commutator between the density matrix and the Hamiltonian. And we said for the cases where the Hamiltonian is time independent, the solution is given by sigma of t will be equal to the propagator e power minus I Hamiltonian t times sigma of 0 times e power I Hamiltonian t. And the solution of this was therefore given by the Baker-Campbell-Hausdorff formula expansion as shown here. So this major caveat of the Hamiltonian being time dependent was alleviated in the next lecture, where we said if you are able to do a similarity transformation where the U would be given as something very similar to the rotating frame transformation that we had done in the classical picture, we were able to see that the transformed Hamiltonian will be given in this form. Here we had actually applied an example where if the initial Hamiltonian has time dependencies in them, let me write the full-blown Hamiltonian where this is the chemical shift part. We saw that in the previous lecture, the transformed Hamiltonian will be given by the offset times Iz plus omega 1 times Ix cos phi plus Iy sin phi. And in the condition that the pulse that is applied has a strength that is constant as a function of time, that is omega 1 being time independent, and the phase is also constant as a function of the application of the pulse, where phi is also time independent. This entire term that was previously time dependent has become time independent. Hence, what we could end up doing, d sigma r over dt can be given by the commutator of the transformed density matrix and the Hamiltonian. So here, once again, we are able to see the dependence is very similar to the Baker-Campbell-Hausdorff expansion, and we will be able to get what we desire. Having reviewed the concepts, let's go ahead and try to see how this can be applied for a simple one-pulse, one-dimensional NMR experiment. So basically, you have a pulse that I will be denoting as a rectangular pulse, where the duration of the application of the pulse is tau p, so that we get a certain desired flip angle, and the power of the pulse will be given by B1, which of course with a minus gamma B1 becomes omega 1, small omega 1, and followed by this you end up detecting the signal over a function of time t. As always, let's take a simple example of a pi by 2 pulse applied along the y-axis. Just to reiterate a little bit of what we had understood the last time, we had, when we are looking at the bulk magnetization m0, we were able to remember that the signal as a function of time came up something of this sort. Let me write the equation. I suggest you to go back and take a look at the previous lectures in case this is not clear. We were able to see that the oscillation and the relaxation part results in a Lorentzian line shape at an offset of capital omega. Here, once again, we'll be seeing the same effect, but from the perspective of spins. For instance, we are trying to define the alpha state, which is going to be 1, 0, and therefore the beta state is going to be defined as 0, 1. When you have something of this sort and your wave function is defined as C alpha times alpha plus C beta times beta, we are trying to ask, what if I try to measure I plus? And from the knowledge that you have gained, you would remember this will be given by the product of the density matrix to I plus. Because there's an overbar so that it's an ensemble average. And the important thing one has to understand here, which density matrix? You would have density matrix in all these different places. So the initial part will be the equilibrium density matrix, which gets perturbed by this RF pulse. And then you have the final portion, which is the acquisition portion. To start this lecture, we will try to define how the equilibrium density matrix is represented. The equilibrium density matrix is defined as nothing but very similar to the Boltzmann's distribution which we had seen earlier, the whole divided by so this is very similar to the Boltzmann's distribution that you had seen before, where it's exp minus E by kBt, the whole divided by the Q factor, which is a partition quotient, right? So same thing we get here. So now let's try to reduce it, and we had seen earlier already the kBt is much greater than the energy difference between the states. Actually, I should write the energy of states En. So therefore, we can expand this such that, remember this is an operator. So therefore, you are going to get E, which is the unitary operator in the n by n space, which we will see in a moment, times minus Hamiltonian by kBt, the whole divided by, since you are going towards matrix representation, this summation transforms itself into the trace. E n by n minus the Hamiltonian of kBt. It is quite important for us to remember and recollect that the trace of any of the I operators was 0, where I equal to x, y and z. We had written the Pauli spin matrices for spin-off system. Currently, we are just working on for a simple system. Let's say we can take a water where you have only one proton that you are trying to detect, in which case you are able to understand the Hamiltonian, which is written as a summation of these operators, would have a 0 trace. Consequently, what ends up happening, the trace would therefore only be resulting from the identity matrix in an n by n for an n by n state, which is going to be capital N, let's say. So what do we mean by this is that when you just have alpha and beta states, you remember that your I operators were given by a 2 by 2 matrix. So you have an identity matrix given by 2 by 2 matrix. On the other hand, when you are having spin states that are coupled with each other, let's say alpha alpha, alpha beta, beta alpha and beta beta. Here you have 4 states, so all the operators will be represented 4 by 4 state. So in this case, the identity will be a 4 by 4 matrix of this sort. So depending upon the dimensionality of the system that you are trying to look at, meaning the number of coupled spins, the trace of the identity matrix is going to be given by the number of spins that you are going to have. So let's just call it capital N. So therefore, this is going to be ending up as E, once again the identity, minus the Hamiltonian divided by N times kBt. And one is able to understand this is just a number, and any transformation that we might do with the operator exp minus ht times the exp plus iht is going to keep this invariant. So all that matters to us is the reduced part of the density matrix, which is going to be given by sigma eq is minus Hamiltonian divided by n times kBt, where n is the dimensionality of the system. So let's once again go back to the water system. You're going to only have the alpha and beta states since you have only one chemically equivalent spin. Your Hamiltonian therefore will be given by omega I times Iz. If you're wondering what if the system is larger than water, then in that case the Hamiltonian will be given as the summation over I of omega small I times Iiz. Meaning, let's say you have a system which is like methanol, I is equal to 1 and 2 because you have 2 distinct protons that are present. So therefore, you will be able to write the Hamiltonian for any case that you want to pursue. So going back, what we wanted to do is to get the trace between I plus and sigma for the simple one-dimensional NMR experiment, where we are applying pi by 2 pulse along the Y phase. And until this point, the pulse is applied, you are going to have the equilibrium density matrix. Then we will be looking at what is the density matrix while you apply the RF pulse, and then finally the density matrix after you have acquired the signal. So these are the three different parts that we will be taking a look at. In the previous lecture, I hope you would remember the transformed Hamiltonian when you apply the pulse will be given by omega I times Ix cos phi plus Iy sin phi. Since we are trying to say it's a Y phase pulse, phi will be given by pi by 2. So therefore, the RF transformed Hamiltonian is going to be given by omega I times Iy. Similarly, the Hamiltonian during the initial portion where you only had, let's say I'm going to call them Hamiltonian 1, rather Hamiltonian 0, Hamiltonian 1 and Hamiltonian 2. So here taking a look at Hamiltonian 1, and in Hamiltonian 0 you would have had omega naught or omega Iiz, which when you transform will become capital omega times Iz, where the capital omega is omega naught minus omega Rf, where omega Rf the transmitter frequency. And the Hamiltonian during the acquisition time is going to be, once again, you're going to be in the rotating frame. Let's only call for the chemical shift Hamiltonian. The sigma 0 is going to be given by minus omega Iz. You can call it omega naught for all practical purposes, but let's go for omega Iiz, and the dimensionality is 2 divided by kBt. Now, once again, if you pay close attention, you realize all these are constants except for this part. In fact, even the negative sign can be taken as a constant. So, what we will end up doing is that we will just represent the density matrix as Iz, the equilibrium density matrix as Iz. So therefore, if you want to get sigma 1, what is that you have to do? You have to apply exp minus h prime 1t times sigma 0 times exp plus I h1 prime times t. And if you might recollect, if you want to pi by 2 pulse, then your alpha is given by omega 1 times tau p. So therefore, this t here is nothing but tau p, and the Hamiltonian 1 is going to be given by omega I times Iy. So let me rewrite this for you. exp minus I omega 1 Iy times tau p, and sigma 0 is Iz, exp plus I omega 1 tau p times Iy. And what we are able to see, omega 1 times tau p is alpha. So this can be rewritten as exp minus I alpha Iy times Iz exp plus I alpha Iy. Now this portion can be expanded by the Bch formula, which is going to be given by sigma of 0, which is Iz in this case, minus I times t times 1 factorial times the Hamiltonian. The Hamiltonian is omega 1 Iy comma sigma 0, which is Iz. And what you are able to see is that the omega 1 is present, t is present, and remember, t is going to be equal to tau p. So therefore, what I'm going to end up doing is to take the omega 1 out, and the product of omega 1 and tau p is going to be alpha. So I'm just going to erase the omega 1 from here and make this portion as alpha. So the next one is going to be I alpha the whole square by 2 factorial times Iy comma Iz minus I alpha the whole cube by 3 factorial triple commutator Iy comma Iy comma Iy comma I. This goes on forever. And we know that Iy comma Iz is going to be plus Ix. So therefore, this is plus Ix. Therefore, this entire commutator is going to be minus I square Iz. How does this minus sign come up? Because you are going to take a commutator of y to x, since it's an acyclic order, that will result in a minus sign, and I will also come, so you get something like minus I square. So minus I square will be plus 1, so therefore you know the whole thing is going to be Iz, and you are able to see you are repeating commutators over and over again. Although it seems a little tedious, you are able to once again see it's nothing but iy comma iz. So therefore, this entire commutator is going to be plus iix. So once again, solve the other portions. You will see that it's going to be cyclic, where you have iz alternating followed by ix alternating. So if you expand it, you are going to get iz, and if I take it common out, 1, you're going to end up having plus I square will be minus 1. So the alpha square by 2 factorial. Next term will be alpha power 4 by 4 factorial minus alpha power 6 by 6 factorial, so on. And then you end up having an I times I, which will be minus 1. Minus of minus 1 will be plus. So if you take plus ix out, you're going to end up getting alpha power 1 by 1 factorial minus alpha cube by 3 factorial. So if you take a look at it here, you're going to have an I power 3 times I, which will be 1. So therefore the negative sign will stay. So you're going to end up having a series expansion of this side. Immediately you are able to observe this is nothing but cos of alpha plus ix sine of alpha. We just said we can do a 90-degree pulse experiment where alpha is equal to 90 degrees. So therefore, your sigma 1 is going to be given by Ix. So what have we done so far? Let's review a little bit. We are once again trying to understand the one pulse experiment where the pulse is applied along the Y phase with a flip angle of 90 degrees on resonance pulse. We started with the equilibrium density matrix which is defined as Iz. Then if you apply the 90-degree pulse, we use the Baker-Campbell-Hausdorff expansion and we find that the sigma 1 is going to be given as Ix. So the only thing that is remaining for us is to understand what happens during acquisition. Therefore, sigma 2 will be given by Exp minus IH2 prime times T sigma 1 Exp plus IH2 prime times T. And what is H2 prime? H2 prime is the transformed operator during acquisition, which is going to be given by capital omega times Iz. So this is going to be equal to Exp minus I omega T times Iz. Sigma 1 is Ix, Exp plus I capital omega T Iz. Once again, if you do the Baker-Campbell-Hausdorff expansion, you're going to get Ix, which is sigma, whatever you started with, minus I, similar reasons, I'm going to take omega t outside by 1 factorial, the commutator, Hamiltonian, comma I naught, plus I omega t the whole square by 2 factorial, double commutator, minus I omega t the whole cube by 3 factorial, triple commutator. And then so on. So let's calculate this again. This will be Ix, Iz, comma Ix will be plus Iiy, and I square will become minus 1, so you're going to get plus omega t by 1 factorial times Iy. So what have we said here? This is going to be Iiy. Iz, comma Iy is going to be minus Ix minus I square. Ix will be the commutator here. So this will be minus I square will be minus 1, so it will be plus Ix. So once again you are able to see this commutator ends up coming back here. So this will be Ix, so there will be minus omega t the whole square by 2 factorial Ix. So this will be Iz, comma, there will be Iiy, I power 4 will be 1. Therefore, minus sigma t the whole cube by 3 factorial Iy and so on. So once again, clubbing similar terms of Ix, you will end up getting Ix times 1 minus capital omega t the whole square by 2 factorial plus capital omega t power 4 by 4 factorial and so on, plus Iy omega t minus omega t whole cube by 3 factorial, omega t the whole power 5 by 5 factorial and so on. If you pay close attention, this is nothing but Ix of cos of capital omega t plus Iy of sine of capital omega t. So now we have achieved our target. What was our target? We wanted to find what is the density matrix during acquisition. And most importantly, we know what is the operator we want to observe. Remember, we said we'll be observing m plus. Similarly, we'll be observing I plus here. And we know the matrix representation of I plus, and we also know the density matrix. So all that we have to do is to take the product of I plus to the density matrix at 2, which we have just determined, and take the trace to see what is that we are going to observe. So let me rewrite it again. We want the trace of I plus to sigma of 2. And sigma of 2 is given as Ix cos of omega t plus Iy of sine of omega t. Great. And our I plus can be written as Ix plus Iy. So therefore, what is the product of I plus to sigma 2? Some might be wondering, why is that I am writing I plus times sigma 2? This will be equivalent to sigma 2 times I plus. This is equivalent to Ix cos omega t plus Iy sine capital omega t times Ix plus Iy. So if you carefully take a product, you're going to get Ix square cos of capital omega t plus Iy Ix sine omega t. Be careful about the order of operators. I guess I'm confusing here, so let me be very careful what I write. Sigma 2 times I plus. This is equal to trace of sigma 2 times I plus. Basically, trace of A times B is equal to trace of B times A is the identity we are exploiting here. So now the other part of it, plus Ix Iy cos capital omega t plus Iy square sine omega t is what we have reduced ourselves to. What is the representation of Ix? H bar by 2, 0, 1, 1, 0. Iy is also equal to H bar by 2 times I, 0 minus 1, 1, 0. Ix times Iy is going to be given by I, H cross square by 4, 0, 1, 1, 0, 0 minus 1, 1, 0. This will be equivalent to, take the product of these two, so you're going to get 1. So therefore, you're able to see that trace of Ix times Iy is 0. Similarly, if you repeat, trace for Ix times Iy will also be equal to 0. The important aspect that you are able to appreciate here is that this can be written as I H cross by 2 times H cross by 2, 1, 0, 0 minus 1. This is nothing but the Iz operator. Okay, so therefore an Iz operator, which we know is also traceless. So you can view the same thing in multiple different ways. So therefore, the Iy, Ix and Ix, Iy terms will not have a trace. All that we have to focus on for sigma 2 times I plus will be Ix square. So why don't we calculate what is Ix square? That's going to be equal to H cross square by 4, 0, 1, 1, 0 times 0, 1, 1, 0. This will be equal to H cross by 4, 1, 0, 0, 1. You are able to see it H cross by 4, E 2 by 2. So therefore, we can actually write this as H cross by 4 times cos of omega t. And similarly, try to work this out as well. You're going to get a 1 by 4 there as well. H cross square by 4 as well. So you're going to get sine of capital omega times t. If you're able to see, we are already arriving very, very close to the answer. So therefore, there is an E in all of these parts. So let me write it outside. So the trace of that is going to be equal to 2. So trace of sigma 2 times I plus will be given by h cross square by 2 e power I omega t. Remember, we have not included relaxation in this entire process, but we can introduce it ad hoc. We are going to get something like this. And therefore, now if you are able to see, the trace provides the result of an experiment where you are able to get the oscillation, and this relaxation part gives the line width. We are able to see here that exactly the same outcome that we were able to get using the bulk magnetization, we are able to get to the quantum state as well. Then you might ask, why do we have to go through something as complicated as this to understand? We will take an example of a two-spin system INS where multiple states should be present, and we will be able to understand, similar to chemical shift that ends up coming, very simply we will be able to understand that scalar coupling will also come in an identical way. Let's try to solve that as an example in a following lecture.